Hi everyone, welcome back. So in the previous video we tried to understand if we replace this IREF by resistor R1, what exactly the sensitivity that we get, and we also simulate the circuit in cadence, and we see the sensitivity was around 11.92 microampere per volt, and also we calculated the value that is also was coming very close to this value. Now what we are trying to do, we are trying to improve the circuit. So here we are trying to obtain a very less sensitive solution compared to this case. So what we are doing, instead of deriving the IREF current from VDD and R1, what we are trying to do, we are trying to replace this R1 by a resistor called M4, and the reference voltage for M4 is generated by M3 from I out. So here you can see this is the I out current. Okay, so this is I out. So this M3 is used to generate the VSG for M4. So ideally what is happening here, so if you ignore the channel length modulation, and we have a factor K over here, as you can see, so factor K over here, so definitely the current I out is basically equals to K times IREF. So I out is basically, this I out is basically K times IREF. And another important point, this equation will hold true for any IREF current as long as you can ignore the CLM. Okay, so basically if you have, let's say, IREF equals to 10 and K is 100, definitely will get 1 milliamp of as I out. If you take IREF as 20, then definitely you will get 2 milliampere of I out. Okay, so this will hold true as long as you ignore the CLM. Okay, but let's see why. So what you can do, you can definitely write the KCL on both side, I mean uh, in this side as well as in this side. So immediately, if you, let's say, if you are applying KCL on the IDF side, you will get this equation, and uh, this is a very straightforward equation, you can see, and immediately you can write. And on I outside also you can write the same thing, and you will get two equation 1, and equation 2. Okay, now you can solve this two equation and you can get the value of Vx and Vy, because here Vx one unknown over here and Vy is another unknown over here. So if you know the Vx and Vy, let's say you can easily calculate I out, because let's say if you consider M2 transistor, so VSG is basically your Vx, and VGS equals to Vx, and VDS is basically Vy. So definitely you can calculate what is exactly I out. Okay, now if you ignore the CLM, means if you put lambda equals to 0 in both the equation 1 and 2, then this two equation will give, let's say, so this is from equation 1 and 2, and these two equation are exactly identical. Okay, so these two equation exactly identical, and you have two only single equation and two unknown. It means you have infinite number of solutions. Okay, so this I out equals to K time IREFs hold for any IREF current, and this is true only when you ignore the CLM, but in real case it will definitely give you one solution. But also you need to note, apart from that particular solution, when IREF equals to 0, that times I out is also 0, that is also a solution. Okay, so zero current is also a solution. For those conditions you need something called a startup circuit to inject some current or to start the circuit. Okay, that we'll discuss later on. So mathematically, I mean, both are correct solution. So you have something called the zero current solution, and another is called a solution that is obtaining from these two equations. Now let us see whether I mean, how much is the sensitivity of this circuit with respect to any change in VDD. Okay, so first of all, if there is any change in VDD, and if your lambda is 0, that time definitely there is no change in IOT. Let's see how. Okay, let's say we have basically, this M4 and M2 are basically current source, right? And M1 and M3 are basically your diodes. So what I am doing, I am replacing that M4 and M2 as a dependent current source. So this is for M4, this is for M2, and we are assuming that On left hand side we have 30 micro of current, on the right hand side we have a factor of K equals to 10, so we have 300 micro of current. Okay, now what will happen if there is any change in VDD? So let's say VDD is increased by some amount, definitely it will increase the current in this branch, it will increase this current, and this current will definitely flow in this way because there is no other part, and that will definitely increase the VY. Okay, so VY increases, it means your VSG will maintain as same, so there will no change. It means your this 30 microcurrent will remain same, because you know this 30 microcurrent or the current through M4 is actually dependent on VY. Okay, or VSG means this one VSG. Okay, so VY changes means VDD increases, VY increases by same amount. It means your VSG is maintained same. It means your current will remain same. So there will no change. But as soon as you consider the channel length modulation, it means you have finite R out on both the side. I mean you have R out this side as well. Okay, this side as well. So definitely whenever you have any change in VDD, let's say VDD increase by some amount, that incremental current will definitely find a path to flow. Like this one you have paths for flowing. So your VY will not increase by same amount, so your VSG will not remain same as before, and because of that if there is some change in VDD, definitely there will be some change in IOT, and we are trying to understand how we can calculate these things. Okay, so that is also very straightforward. So we have this circuit and we have two unknowns over here, one is Vx, another one is Vy. So the same thing we are doing, we are trying to write the equation on both on IDF side and the IOUT side, and that is also very straightforward, that you can just look at and understand. So from these two equation, this one and this one, from these two equation you can definitely write this matrix. And finally, what is incremental IOUT over here? Incremental IOUT, basically you have that Vx over here and Vy in the drain side, so Vy over here. So definitely your IOUT, incremental IOUT is basically GM2 Vx plus GO2 Vy. Okay, so I have this circuit in cadence. What I'm doing, I have a small AC component over here in the supply voltage, and I'm trying to see the response on this node, on this current. Okay. So this is the plot, what I'm getting, this around 6.01. and now let's see from the calculation what we can get. So I extracted the value from the DC simulation. So these are the GO and GM of all the transistors from 1 to 4, and definitely you can put all this value and solve for this particular matrix, and you will get a relationship like Vx and Vy like this, which is dependent on VDD. Now what you can do, you can put all this Vx and Vy in this equation, and finally you will get something called IOUT by VDD. Okay, so that is what I'm doing. So I have GM2 and GO2, so I need that quantities over here. So from there I'm calculating what is IOUT by VDD. I'm getting around 5.62 microampere per volt. Here what I'm getting 6.01, that is very close by. So that is how you can verify the equations as well. Okay, I hope you understood ki this circuit is also sensitive, but it is compared to better, I mean it is better than if you just use a simple resistor. Okay, thank you for watching.